We are now going to start talking about how you can combine multiple capacitors together. Now you might wonder, well, why would we want to do this? Well, it actually comes up a lot for circuits. And in general, you might not always want to combine multiple capacitors together, but you're frequently going to want to combine multiple components together. Light bulbs, resistors, capacitors, batteries, motors, so on and so forth. And so we're going to start by thinking about this with capacitors, but the ideas we're talking about right now are actually going to be relevant for everything we talk about with circuits. So what we're showing here is kind of moving towards a circuit diagram. We're still showing something that looks a little bit like a battery. It has an EMF, which is why it's labeled with a curly E. And then you notice these three things that are labeled C1, C2, and C3. This symbol here means that it's a capacitor, not necessarily a parallel plate capacitor, but this is the symbol we use. Note that we have a special symbol we use for a battery, but we're not showing it right now. And what's happening here is that we're showing three capacitors joined in parallel. So each of these lines is basically representing a wire. And so we have one wire that's coming out of the battery, but then this point here we call a junction. And at this junction, you can see that this wire is actually connected to two wires. And so we call this going in parallel, that when this wire comes here, it again has two different paths. So if you imagine, say, little people or electrons, whatever you want to think about, marching down here, some of them can go this way and some of them can go that way. It's like going to get food at a buffet and having two different lines to go in. Each person goes only through one line, but then at the end, maybe there's like dessert over here. That's definitely a cake with vectors on top, that you come back together, right? So this is what we call parallel, the notion that there is two different paths to choose from. Starting at an initial point, you choose one of them, but then they come back together. But notice here that we actually have three. We would say that all three of these capacitors are in parallel. So these are parallel capacitors, which is different than calling them parallel plate capacitors. Again, here we're talking about an electrical way of connecting them together, not what their actual shape or configuration looks like. And I'll contrast that in a little bit for a different way of connecting them together. Note that again, if we think about these capacitors being like attached to wires, the end of each wire is actually connected to the same spot. This is a circuit. Again, you should recognize that this is a battery, and we again have three capacitors. Now they're joined in series. And earlier when we talked about batteries, I also talked about batteries being attached in series. And in this case, again, imagine, if you will, a person walking along the wire. The only choice you have is to first go through C1, then go through C2, then go through C3. You're going to walk through all of them, but you don't ever get to choose. You have to walk through all three of them. So that's what we mean by series. Now, there are some interesting physics things to think about in these two scenarios. And I'm actually going to summarize in a little bit, but let's go back and look at parallel. Let's think about potential. And again, this is a wire here, and we're going to assume that this is effectively an ideal wire, which means that it's a conductor, right? So this is a conducting wire. And something to remember about any type of capacitor, look at what's happening inside. There is no wire. So what this should tell you is that if I have, say, V plus up here, that at a different spot on the wire, I also have V plus. Now this is of course assuming electrostatic equilibrium. So for now, I'm going to assume that electrostatic equilibrium. And so we're going to say that our potential is the same everywhere on the conductor. So that means that one side of the capacitor is all the same, because again, it's connected by a conductor. And if we assume that these are charged rather than charging, we get to say that. So this wire, this conductor, is all at the same potential. But then at the other end, we have V minus. And again, notice that this wire here comes all the way up to the bottom of these. And now typically the negative side of a capacitor we call 0 volts. So I can go ahead and say that this is actually 0 volts. And so note that across each one of these we have the same delta V for every single one of these. And it's just the nature of our conducting wire. So whenever you have parallel capacitors, the potential difference across all of your capacitors here are the same. And that's again because the same sides are connected by conducting wires. Our situation in series is different. We don't actually want to think about potential now. We actually want to think about charge. So imagine that we've had some net charge come out and end up on this side of this capacitor. So because we have positive charge on that side of the capacitor, we want to have negative charge on the other side of the capacitor. But where will that negative charge have actually come from? Well, the only place that negative charge can come from is if actually it is separated from some positive charge. Why? Because if we imagine just this segment, it's isolated. This must be neutral. So while we can separate the charges on it, effectively polarize it, we can't make net charge appear. So that's going to be true for this next segment as well. So if I had positive charge on the top plate of C2, then I again have negative charges appearing on the bottom plate, which again means that I have some separation occurring, and I'm left with charge again on the top of C3. So note then that I'm left with negative charges on the bottom, which is fine, that's connecting to the negative side of the battery. So this is a way to think through the fact that the Q on each of these is the same. So what's important to recognize if we talk about the differences in potential across them, they are not necessarily the same. You can have different size capacitors. The same delta Q means that you actually have different delta V's. So whenever you have series capacitors, you want to think about charge. Whenever you had parallel capacitors, you wanted to think about potential. So to briefly summarize, when we have parallel, we say that the delta V is the same, and that then allows you to relate the different charge on the capacitors based on the fact that they might have different capacitance. There's then a way to combine them together, which we will talk about in actually the next video. But we're going to combine it down to one capacitor, which is then our equivalent capacitor. In the case of our series capacitors, we again said that the Q's must be the same, but the delta V's aren't necessarily the same. So we use those delta Q's to relate potentially to different values of capacitance to get different delta V's across each capacitor, knowing that the total delta V here from the top to the bottom must come back and equal the EMF across the battery.